Okay, next we will continue our discussions regarding several methods or numerical solutions for solving the linear system of equations. Previously, we've talked about how a numerical linear solutions or methods for solving linear systems using direct methods, in which especially we are discussing about the Gauss elimination methods. Now we are going to discuss another method, so-called the LU factorizations methods, in which we're focusing on the Doolittle methods, which basically the purpose is quite the same with what we have for Gauss elimination method, in which to solve the linear equation systems. Okay. Well, a little bit general explanations about these LU factorization methods. Well, basically, we have discussed about these methods were used to solve a linear equation system, in which can be represented in a form of matrix multiplications of A multiplied by X equals B, in which if you go back to the previous videos or previous slides, we can represent mathematical formulations of a linear system, which can be shown like this: a11 x11 plus a12 x sorry, not x11 but x1, and then x2 plus something's a1n multiplied by xn equals to b. And then we have several like this: a21 x1 plus a2 2x2 plus something's a2 and xn equals b2. The previous one was b1, until we have a n1 x1 plus an 2x2 plus something's that a and n xn equals bn. And then this can be represented into a form of matrix, in which you will have a matrix. Let's say here's the matrix A multiplied by the x here, and then equals to B. Right? A, this one the x value, this one is the B value. So A will represent all the coefficients of the A value here on the left hand side. X will represent the variables that we are going to find for a linear equation systems, and B will be represents the right hand side. Okay. In the Gauss eliminations approach, we're trying to transform this matrix, in which we will represent it in the form of a augmented matrix like this one. Sorry, like this. Like this one. This one we have the A part over here, and then the B part over here. Put it on the right, something like this. And then in the Gauss transformations, we're trying to like make this upper part, the A part, to become upper triangular matrix, in which we want to have all the values in the diagonals of the A will be equal, will have value, and then the one that below that diagonal will have 0 value. Yeah, this one, upper triangular matrix. So all of the value below these diagonals or something, and then 0, 0, and then something, so until here it will be 0. Okay, and the rest you can substitute it back, and then you get the value. Right. In order to do this, you will need to do several we call it elementary row operations, so that it will be easier to substitute back. Okay, with the same principles, actually we can reduce the amount of calculations that we need to do by assuming that if we can factorize this A matrix into two matrices called L and U, so LU, then we can still have the same linear equations. So basically, instead of just transforming one matrix here, matrix A, into the upper part, so now you are going to try to work on two matrices in which you create you transform the A matrix into two matrices called L and U. Okay, and then how would you substitute it back later on? Okay, we need two steps before we can substitute it back. So now, after we assume that A will be equals to LU, then you can assume another one. So by letting, now you have L multiplied by U multiplied by X is equals to B, right? Now if you assume that U multiplied by X will be equals to Y, okay, this one, oh sorry, U multiplied by X is equal to Y, then you can substitute using two steps by solving the formulations of L, because this one is Y, right? Ux is Y, so L multiplied by Y is equals to B, then you get the value of Y. And then in order to get the value of X, because you have U multiplied by X is equals to Y, then you can substitute it back, you get the value of X. Okay, that's the concept of LU factorizations. I think this concept will be much clearer if we directly go to the example. Okay, now we move on to the example. Okay, oh, before that, maybe more detailed explanation. So basically, in the LU factorization methods, especially the Doolittle factorizations, basically you just want to transform. The first step is to have the A matrix equals to two matrix, which is L and then U, which L will be a lower triangular matrix, means that all the diagonals consist of one value, and then U will be the upper triangular matrix, in which we can generate using the same approach which we have in the Gauss eliminations. So for short, you have in detail A equals LU means that we have matrix A like this, and then you will convert it into matrix L and then matrix U here, okay, which L will be a lower triangular matrix where all the value of their diagonal here is equal to 1, and then U will be upper triangular matrix in which all the value below the diagonal will be 0. Okay, this can be generated by Gauss elimination approach. What about this? Okay, this will be generated along the way with you generate with for the U matrix. What do you mean by along the way? Okay, you can see it in a moment in the example. Here we have the matrix A right here, right? And then we're going to generate matrix U and L. Okay, I know this is already shown the answer here. However, assume that you don't have the value of this one first here. Let's assume that you don't have this value. Sorry. You don't have this value first. Okay. You don't have this value. You don't have this value. Okay. Assume that you only know that this will be the lower triangular matrix in which all the value up from the diagonal here will be 0, and then all the value of the diagonals, this one will be 1. Okay, so here this one will be 1. Okay, right? Okay. Meanwhile, the other matrix, the U matrix here, this one, okay, we will try to generate it from A, this one, A. Okay, so you are going to create the U matrix from A by a Gauss eliminations approach, like I mentioned earlier. This one, Gauss elimination. Meanwhile, this one, the L matrix, we create along the way when we create the U matrix. Okay, let's focus on the U matrix now. Okay, in order to create a Gauss U matrix using Gauss elimination, I think you should go to the previous video to see if you forgot how using the Gauss eliminations to create this. The first one is to select the pivot value, the pivot row, in which for now we select this one because this is already 1, and then our job is to get rid of this one to become 0, right? Okay. The first one, of course, okay, you select this one as the pivot. So to get rid of this, so you will have the calculation is that by doing the new R2 value would be equals to -2 multiplied by row 1 multiplied by plus the old R2 value, right? So here's you will have 1 multiplied by -2 plus 2 will equal to 0. 3 multiplied by -2 minus 6 plus -1 equals -7. 6 multiplied by -2 plus 1 is -11. So you get the new value of row 2, okay, which is this one. Now you can see the connection between L and U matrix is that when you use the multiplication here by -2, this one, you're actually going to use this -2 here in the L value here. You see, the -2 here were the value of the opposites of this one. -2 multiplied by -1, you get 2 value here. Okay, that's what I mean along the way. Okay, meanwhile, the U matrix, you already have it here, correct? This one, this, the new value of it is here, correct? So what is the next step, right? The next step is you're going to eliminate this part, right? Okay, this part, make it become 0. How do you eliminate this? Become 0. So you're going to use what? You're going to use this formulation. So the new value of row 3 will be equals to minus 4 multiplied by row 1 plus the old value of row 3, right? So you have 1 multiplied by minus 4 will be equals to minus 4 plus 4 is 0 here, right? And then 3 multiplied by minus 4, minus 12, plus sorry, not this one, plus 3 multiplied by minus 4 plus 4 plus minus 2, so minus 12 plus minus 2 will be equals to 14 here. Okay, correct. So previously you got 0, so now 14. Now the last one, 6 multiplied by minus 4, minus 24 plus 3 is equals minus 21. Okay, now you got the last row already done here. So, okay, so now you obtain this one. Basically, to get rid of this one, now you get the well, partial for the u before u matrix before it become to this one. We still have one more steps to go from this to this. But you also at the same time updating this part in the L value. Remember, we create L along the way. So this one, how do you get rid of this 4? By multiply the first row with minus 4. So you get the opposite of minus 4. Minus 4 multiplied by minus 1, put it here. So you get 4. Okay, minus 4 here, 4. This one minus 2, you get 2 here previously. Okay, now we are not yet get here the u. We're here now on the second one. Now what is the next step for make from this value, this matrix, to become the u matrix here? If you still remember, we're going to need to remove this part, right? Remove this part and then you can get it become 0 here like this one. Okay, now what you need to do is that to get the new value of this one, you will have the row 3 will be equals to, you select the second row as a pivot row. So minus 7 minus 14, you get minus 2 multiplied by row 2 plus the old value of row 3. Correct? You can see now the calculation here. This one still 0 here. Okay, this one minus 7 plus, multiplied by minus 2, 14 plus minus 14, so becomes 0. Then now minus 11 multiplied by minus 2, 22, and then this become to 1. Okay, then you see that here, sorry, not this one. To get rid of this for minus 14, you use this minus 2, right? Then it's corresponding to this value in the L matrix. So how do you get this one? Is the opposite of minus 2. Minus 2 multiplied by minus 1 equals to 2. Okay, now you will get the final form of the L, the U matrix here, as well as you get the final form of the L matrix here. You can see. So we generate the U matrix using the Gauss elimination, and then L matrix along the way when we generate the U matrix. Now we got the L and then U matrix. What's next? Next is that we will substitute it back like what we mentioned in here. We have the L and U matrix. Now we use the L matrix to get the Y value, and then U matrix to substitute get back to the final value variables that we are going to find is the X value. Okay, now let's move on. This one, okay. Okay, we're going to go this one later on. Okay. When we have the L value and then U value, L we will use to substitute back, or we call it forward substitutions, to get Y. And then X we will use to do a, after we get the Y value, we will use a back substitutions to get X. Okay. Now let's see from the previous examples, we already got the L and then U matrix for this A, right? Previously, we get the L matrix using the Doolittle factorizations. We have the L value. The L was 0, 1, 1, 0, 0, and then here's, of course, this one will be 1, and then the last one is 1. This one also 0, right? From the factorization earlier, we have this one 2, this one 4, and this 4. This one is 2. This is the L matrix. What about the U matrix? We're using the Gauss eliminations, where we got this one still 1, 3, 6, and then previously we get rid of this one of 0, become this one is -7, and this one is -11, and this one is 0, this one also 0, this one is 1, correct? So you got this L and then U. Okay. Now the first step is doing, okay, we have this L and U. Now we do the forward substitutions to got the value of Y. As you remember, this one, L multiplied by Y is equals to B. The B value is here, okay, given from the questions. So you plot the value of the L here, okay, sorry. The L matrix is here, and then multiplied by Y, okay, and then here's we have the value of P. P is from the questions earlier, okay. And then now if you do forward substitutions, means that this one represent what? 1x1, 1y1 multiplied by 0y2 multiplied by 0y3 is equals to 3. Means that we have y1 is equals to 3. Okay. And what about the other one? This one means that 2 multiplied by y1 plus 1 multiplied by y2 plus 0 multiplied by y3, right? So here's the second one, we have this formula. And finally we have the last formula. Here's 4 multiplied by y1 plus 2 multiplied by y2 plus 1 multiplied by y3 equals to 19. Okay, now based on the forward substitutions here, we can have like y1 is equals to 3, then we substitute y1 to here's 3 multiplied by 2 is 6, 9 minus 6 is equals to 3 as well, so y2 is equal to 3, this one, y1 is 3, y2 is 3, now you substitute it back here, and then the last one, 3 multiplied by 4, 3 multiplied by 2, and then you get how many? 18. Y3 will be equals 19 minus 18 is equals to 1. Okay, that's forward substitutions. Is it finished until here? No, of course. Now the second one, you get to do the backward substitutions, in which you have u multiplied by x equals y. U is what? U is this one. okay, which is this, multiplied by x value here, which is equal to y. Y is what? Y is this one. Okay, so finally you can do the substitution like this. So now you have like 1 multiplied by x1, 3 plus 3 multiplied by x2 plus 6 multiplied by x3 is equals to 3. The second formula is that minus 0 multiplied by x1 minus 7 multiplied by x2 plus minus 11 multiplied by x3 equals to 3. And then finally x3 is equal to 1. Okay, now you backward substitutions, you put x3 here, so minus 11 become 14, minus 7x2 is equal to 14, so x2 is equal to minus 2. Then you substitute it back to the first equations, you will get x1 equals to 3. Okay, then you can finally solve the equations, which here you got the value of the x is x1 equal to 3, x2 equals to minus 2, and x3 equals to 1. Okay, then that's about the Doolittle factorizations. I know some of you may think that, oh, this one is even longer, take us longer to calculate because we do the Gauss calculation as well as two times substitutions. However, in terms of calculations using computers, actually we can do the factorizations directly instead of doing the Gauss eliminations. Assuming that okay, this one is another one. Okay, you do the factorization directly, so you will calculate it based on this formula. So basically, if we have the setting a is equals L multiplied by U, so a is this one, L multiplied by U is this one, right? In terms of the, because if you combine both of the L matrix, which is the upper triangulars, lower triangulars, and then U matrix is the lower triangulars. Go back here, this one. Okay, if you multiply this with this, correct, you will got this new matrix, this one. Okay, so this is A, this is the other on the right hand side is multiplied by L multiplied by U. Now you can pair it one by one. So you have U11 will be equals to A11. U12 is equals to A12. U13 is equals to A13. Okay, make it clear a little bit. This one will be equal to this, right? Meanwhile, this one is equals to this, correct? And this one equals to this one. Okay. So when you want to get the value of the, let's say this one, A21 were equals to L21 multiplied by U11. So if you plot this value, right, you know the value of this one. In order to get the lower matrix here, L21, it will be equals to A21 divided by U11. Because you already know the value of A21 here, A21 of course you already know, but U11, what is U11? It's here, A11, right? So you will have the value L21. And so on, you can generate all of the formulation for the L as well as the U value here. Okay, this is what we call the direct calculations. So basically, using these direct calculations, you can have this value of the L and as well as the U. Okay, so basically you will first calculate this value U11, U12, U13, and then for the L21 you will generate it based on this formula, and then you generate U2 U23, okay, because you already get the L2 value. And then based on this, you generate this L31, okay, based on what? Based on this formula, okay, because you already get U22 and U23. And then you generate the U33 based on this formula, because you already have the L31. Finally, L32 will be generated based on this formula. Okay, so those are the direct calculations. Soon after that, you get the L and U value. Then you can go back to calculate using the forward and back substitutions. Okay, the same example here. Okay, the final content of this slide is the Matlab function. This consists of two. First is the Doolittle factorizations. These factorizations will allow you to get two values, the L and U, this code. Okay, so basically the L and U value is to create the upper and triangular by using what? By using the direct calculation. We're not using Gauss elimination here, but using the direct calculations. Okay, and then after that, we're finished with the Doolittle factorization after get L and U, and then you will going to use this one. Okay, you use the Doolittle's methods or LU factorization using Doolittle factorization, in which inside of this code you can see that here we call the functions that defined earlier, which is the Doolittle factorizations of the matrix A. You have L and U, and then finally you just need to do the forward substitutions in this part as well as the back substitutions. So finally you will get the value of X. Okay, I think that's about the code. Again, I will not go to in details for this approach. You can try it in your Matlab's programming language, and I think it should work. And okay, I think that's all. We have discussed the Gauss elimination earlier in the previous video, and then LU factorization using Doolittle's. I think that's already quite a lot of materials for you as for now. Later on, if we have some more time, we will discuss the rest of the methods. However, we will try to introduce you to a Matlab first, and then we move back to the materials as we go. Okay, thank you.